good. Should be good. I don't know what's going on. I don't know what's going on. I don't know what's going on. Na 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 I don't know what's going on. So let's play with the settings. Echo. Why would echo cancellation reduce mic automatically adjust? No. Oh, now it's coming. Don't adjust. No adjusting. 1, 2, 3, 4, 5. And it's wait, it's not going. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Reduce my background noise. I don't care. 1, 2, 3. Don't do echo cancellation. I don't want it to do anything. So do nothing. Right now, everything is checked off. Oh, look at that. It goes away. The audio goes away. So let's add echo cancellation. Added echo cancellation. Added echo cancellation. Okay, now it's okay. It sounds okay now. Important, do not turn this off unless you have a high quality microphone and are wearing headphones. Don't have any guests. This setting enables audio processing features like echo cancellation, noise suppression, audio gain control. Podcasters and musicians often turn this off. Yeah, who does? Podcasters, yeah. I want this off. So if I turn it off, does it still work? 1, 2, 3, 4, 5. Now it's off. Echo off. Now that the echo is off, let me raise the mic to maximum. 200% microphone. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, nothing. Oh my god, this is so strange. I don't want it to do anything, but I have no choice. So with echo, improve audio clarity by minimizing background noise. Automatic, just mic. I don't automatic mic. I don't know. I don't know. 1 audio mic is at 100. 1, 2, 3, 4, 5. Okay, so we have echo cancellation on. Reduce mic. Okay. Okay. Mhm. I can't even end the stream and restart it because it's gonna the whole problem starts over. So every time we have to waste the first 5 minutes. Absolutely atrocious. Okay, so somebody, let me share this with you. So somebody said that they want me to interview them. No, that's not it. This is it. Wait, is this okay? Yeah. So he said that he wants me to interview him. Um, let's go. Uh, wait, I want to maybe also.
Welcome to Real Physics. This is
His
about it.
audio is always terrible. Unzika. Let's ask him if I can interview, view email address. Okay, so bus, verify. Okay, submit. There's his email, copy email. Okay, let me send him an email. Is this my email? I think so. Compose to email. I would like to interview you for my channel. And let me give him my channel. What is my channel? Can I give him a link to my channel? View your channel. What about just sharing my channel? How do you share my channel? Okay, I guess this is it. No, this is it. So it's copy clean link. Where's the Gmail that I'm writing him? Hi, Dr. Unzeker. I have a small YouTube channel. I have been watching you for years. I have been doing a deep dive into modern physics lately. I would love to interview you. Would you be interested? Here is my channel. Well, they wouldn't know. We have to do /live. Is it /live? Is it /live? How do I share specifically the live? So I think we just need to go to the live. Yeah, streams. Okay, this is what I should give him. This is what I need to give him. Here's my channels, live streams. Here are. Okay. Send. Okay. We shall see. We shall see. We shall see if he is interested. La 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 la. Okay, we're getting everything set up. Fan. Oh, Woody has a message for us. LOL. Okay, nothing. Okay, what's the next order of business? So what are we doing today? We are doing reading more Einstein's original stuff. So remember what my purpose is. My purpose is to figure out quantum mechanics because I've figured out special and general relativity. I'm very confident about these. I'll make videos here and there expressing my disdain for where everyone is wrong. I think I've already expressed it. I could make short videos. We'll maybe do those just for, just to wake up when I'm tired. But right now we need to go back, I think. I was thinking maybe to continue the course in general relativity. I took some time to study a little bit of mathematics because something came up during the course in general relativity that I had to listen to about something else. Okay, let's shut down everything. I think we should do, because what I'm interested in as far as general relativity is concerned, what I'm curious about, I want to see where the curved geometry comes from, where this mistake comes from. I want to see exactly where the mistake comes from. I want to understand the equations, the field equations of GR, so that I can understand exactly where the problems come from. So let's try doing that. So instead of reading more of Einstein, we'll be doing just the GR course. Okay, so the GR course, this we don't need this. Just closing some windows. I'm not gonna do Lorentz transformation. I don't know what's going. No, I wanted to know. Yeah, I wanted to know. Okay, before that, so let's go back to Lorentz transformation. So Lorentz said that he can prove that. So Lorentz said that he can prove that uh, that the electron or the electron cloud, but maybe even the electron from Maxwell. Maxwell never discussed the electron. Maxwell is not particle physics. In Maxwell's equations, there's just fields. So the fields are not quantum. There's no particles. There's just the wave equation of electromagnetic waves. So let's maybe listen a little bit to the Lorentz transformation. Unfortunately, I think all they're going to discuss is just Einstein's relativity.
There is above all the speed of light, the speed that sprang from Maxwell's equations, the 300,000 kilometers per second that Michelson measured with landmark accuracy, the speed which is essential in modern physics and vital to understanding the universe as it really is. And at the end of the 19th century, when Lorentz derived his transformation equations, when it came to speed, the most moving human experience was provided by trains.
Okay.
Big or small, sophisticated thing on Earth that moved people faster. And it may not be aware of the speed, but since the time of Aristotle, the ether out to prove once and for all that what was then, and their goal was to detect motion through the ether by measuring its effects on the speed of light. In one attempt after another, with the most sensitive experimental device ever constructed, they found exactly what they weren't looking for. The interferometer showed that, regardless of the motion of the observer, the speed of light.
This is an interferometer. It measures interference.
Same. For Michelson and Morley, this was bad news, and it traveled fast as a boat could carry it, to Ireland. There, physicist G.F. Fitzgerald, an early champion of Maxwell's electromagnetic theory of light, examined Michelson's otherwise disappointing results. Fitzgerald's explanation was that in its motion through the ether, one arm of the interferometer was contracted by a fraction of its...
That's genius. To come and say that one arm is being contracted by the motion through the ether, and no one was paying attention to this. This is a mechanical explanation. Einstein never gave a mechanical explanation. In his explanation, we're not moving through the ether. The ether is stationary. That's nonsensical. That's unscientific. That creates so many paradoxes. I tried so hard to have a stationary ether. You can't. I couldn't do it. So the ether must be flowing through us, and it is gravity. That's my opinion. So the direction they were pointing was wrong, but it wouldn't have helped them because it still would have compensated. The clocks slow down. Wait, this is not about clocks. The arm gets shortened because this is not about clocks, because we're comparing two beams that emanate from the same source. So this is not about a clock. This is just about the speed of the waves. But if the arm is shortened by just a little bit, that compensates.
its length, which was just the right amount to allow the two light beams to arrive simultaneously.
That's incredible that he said it. I mean, this is length contraction just out of intuition.
Immediately, most scientists scoffed at it.
And this is because he was an expert in Maxwell. So he saw it in Maxwell. How do you see length contraction in Maxwell? How do you see length contraction in Maxwell? What are you talking about? I'm trying to think about Maxwell. Maxwell electrodynamics? It's just the electromagnetic wave? How do you get the length contraction? I don't get it. So the ether is obvious in Maxwell. I'm just trying to think through this. The ether obviously is the basis of Maxwell. Yeah. Wait, let me take some water. This is I'm so curious about this. I mean, this is the Fitzgerald. This is already somebody else. This is Lorentz, who was supposed to be the greatest physicist of the time. Um, but Fitzgerald had the intuition that one arm is getting shorter by just a little bit because the discrepancy is supposed to be tiny. I'm wondering, I've never done the geometry. I've seen lectures about it, but I never actually looked into it. So the question is, how do you get a length contraction from Maxwell? Maxwell is just a bunch of experiment put into mathematical shorthands. How do you see? I'm trying to think. How do you see that if you move fast through the ether, the faster you move through the ether, the more you contract in relation to the ether, you become shorter? Why would that happen? Fascinating.
The idea. However, when Hendrik Lorentz arrived at the same idea, no one was laughing. Not only was he the world's expert on Maxwell's electromagnetic theory, but Lorentz gave a tangible explanation for the contraction phenomenon.
Tangible. So the greatest mind in Maxwell's equations had a tangible explanation, and everyone just ignored it and went with Einstein that never explained anything, just said these are the postulates.
He thought it had to be a property of the electron, whose existence had just been confirmed by J.J. Thomson and his colleagues in England.
It had to be the property of the electron? That has nothing to do with Maxwell. Maxwell discusses fields. He never discusses quantum phenomenon.
It seemed that in electrons, they found the inner parts of atoms, the ultimate constituents of matter, but they hadn't discovered all the things that electrons actually do. One possibility, Lorentz believed, is that an electron will contract in the direction of motion.
An electron will contract in the direction of motion. Can somebody please prove that?
That were true, and since everything is composed of electrons, then an interferometer would contract in the direction of motion.
This is unbelievable.
So would a ruler, and so would a locomotive. While length contraction took care of the Michelson-Morely experiment, Lorentz knew more was needed to explain all the experiments that had failed to detect motion through the ether. Since he still believed in the ether, and the fact that the Earth moved through it, he felt that somehow the electron must be responsible for this amazing fact about light. Regardless of the speed with which they themselves are moving, all observers measure the same speed of light. Certainly others.
Wait a minute. Can we prove that there is length contraction? Can I prove length contraction? I can prove time dilation. That's easy. But why would there be length contraction? So that has to come out of first principles, meaning out of Maxwell. I mean, I wouldn't. Why would there be length contraction? I'm trying to think. I mean, time dilation is easy, but why would you get length contraction?
Other speeds, say the speed of a moving train.
Einstein just postulated length contraction. He just said it has to be in order for his first postulate to always be true, that the speed of light is constant for all observers.
Are the same to all observers. On a platform, for example, this train's passing at a good clip, but to someone on the train's speed seems to be zero, and the ground outside seems to be moving instead. Therefore, as Galileo was well aware in the Renaissance, and as this fellow knows today, the speed of an object depends on the observer's speed. But Lorentz said that perceptions of light waves would be radically different. He suggested that even someone traveling at nearly the speed of light would still observe light moving at 300,000 kilometers per second.
So this is basically Einstein's theory of relativity. So Lorentz already proposed time dilation and maybe length contraction. So all that Einstein did, Einstein took a few more steps forward. He created E equals mc squared and mass increase, relative mass.
How could that be? Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light
that's time dilation.
Each
This is true in every medium. This has nothing to do with light. You don't have to be an expert at Maxwell's. You can just understand waves. Who created the wave equation? So this is just a wave equation.
believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart.
Wait, Is it wave equation? No, it's simple geometry. It's simple wave geometry. Everything here is simple wave geometry and can be reproduced with sound with any wave.
How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. In reverse. Disagree on whether events happen simultaneously. A petty debate. It means that time, as well as distance, has to be effectively objected to the limited nature of Lorenz's explanation.
It has to do with your internal clocks. Because we are made out of because we wave through the ether. We are ether waves.
What was needed, he said, was a new fundamental law of physics, the principle of relativity, according to which the laws of physical phenomena should be the same, whether for an observer fixed or for an observer carried along in a uniform movement of translation. In other words, as Galileo had suggested, one state of uniform motion is as good as any other. After all, this idea was the basis of Galileo's reasoning and the law of inertia, almost 300 years.
This can be so easily understood as water waves. If you just play the game with the water waves that we started explaining, that would be the best. I think that would be the easiest. Let's go check the audio of the current recording. Where is the audio? Oh, I shut it down? Oh my God. Let me reopen it. Gotta go to sleep soon. I'm dead. Yeah, audio is good. Very good. Good audio. Okay, we're up to 173 subscribers. We're growing steadily. Very nice. All right.
Earlier. But Poincaré was suggesting that the idea of Galilean relativity should be generalized.
Let's check. Is there anyone watching? Oh, 2 people are with us. So let me give you the link. If anybody wants to join, you're welcome to join. Click the link and you'll be joining me and we can have a discussion. I'd love to do that. Let me also tell everyone on Discord that they can join me. Okay, here it is. Oh, we have 2 people, Alif Null and Andrew. Vegan Gains, Sheep for Life. Okay, we've welcomed everyone. We didn't welcome this guy. Did I wave this guy? Wave, 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 wave. Okay, everyone has been waved. One new message. Why? Join me. Da 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 da. Da 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 da. Okay, so now we have 0 people. They ran away. They don't want to join us. Oh my God. All right, let's continue watching.
To include all physical phenomena, including light. For example, an observer could not determine whether he was in motion by measuring the speed of light, since that speed is the same for all observers. And that meant age-old notions about time and space had to change. And though Poincaré himself shied away from examining the consequences, Lorentz...
Who was Poincaré? I didn't catch that. I need to write a timeline of all these names.
This idea was the basis of Galileo's reasoning and the law of inertia, or for an observer carried along in a uniform movement of translation. In other words, as Galileo had suggested, one state of uniform motion is as good as any other. After all, this idea was the basis of Galileo's reasoning and the law of inertia almost 300 years earlier. But Poincaré was suggesting that the idea of Galilean relativity should be generalized to include all physical phenomena, including light. For example, an observer could not determine...
What Poincaré? Where did they mention Poincaré? I didn't catch that. Poincaré. What did Poincaré say? I know the last famous person they mentioned is Lorentz.
was well aware in the Renaissance, and as this fellow knows today. He felt that somehow the electron must be responsible. So would a ruler, and so would a locomotive. While length contraction took care of the Michelson-Morely experiment, Lorentz knew more was needed to explain all the experiments that had failed to detect motion through the ether. Since he still believed in the ether, and the fact that...
So Lorentz had the notion of length contraction. We still need time dilation and mass conversion.
The Earth moved through it. He felt that somehow the electron must be responsible for this amazing fact about light.
So he felt, but he couldn't derive it, could he?
Regardless of the speed with which they themselves are moving, all observers measure the same speed of light. Certainly other speeds, say the speed of a moving train, aren't the same to all observers. To an observer on a platform, for example, this train
Mm.
is passing at a good clip. But to someone on the train's speed seems to be zero, and the ground outside seems to be moving instead. Therefore, as Galileo was well aware in the Renaissance, and as this fellow knows today, the speed of an object depends on the observer's speed. But Lorentz said that perceptions of light waves would be radically different. He suggested that even someone traveling at nearly the speed of light would still observe light moving at 300,000 kilometers.
That's incredible. So Lorentz already said that someone moving near the speed of light, so he already felt that it's impossible to go faster than light. Why would you say that? What indication do you have that it's impossible to go faster than light? Why would you say that? Why would there be a speed limit? Why would the speed of light be any speed limit? Why would that be? I mean, I have the theory for that. No one else has proposed the theory. Why can you not go faster than the speed of light?
Per second. How could that be? Consider two observers in relative motion.
All they can say is, well, we assume that the speed of light is a constant. All right, but why is the speed of light is a constant? That's just because it's a wave. Okay, so, but there's such a mess. It's like there's no. It's not like there is a complete question answer. It's not. We've never answered all these basic questions. It's like everyone is always jumping to conclusions and never really going through a rigorous proof of the previous step.
Albert and Henry, just for the sake of argument. Fear of light expands
Where's
outward,
Poincaré?
always at the center of that. To confirm, however, while Albert, but they disagree on whether this is not so. However, as profound as this was, the French mathematician Henri Poincaré objected to the limited nature of Lorentz's explanation. What was needed, he said, was a new fundamental law of physics, the principle of relativity, according to which the laws of physical phenomena should be the same, whether for an observer fixed or for an observer carried along.
That's incredible. So he said all the laws of physics. It sounds like so Poincaré. I don't think Einstein mentioned Poincaré in his seminal 1905 paper. So, but this is genius. So he said we need a new, like we need to redefine basically Newtonian mechanics for the speed of light. This is incredible. So this is all because of the Michelson-Morely. And they never neglected. They never said we need to get rid of the ether.
Motion. However, as profound as this was, the French mathematician Henri Poincaré objected to the limited nature of Lorentz's explanation.
Oh, it's a limited nature. So, because there's only time dilation and length contraction, there's no mass. Mass what? Mass increase, I guess.
What was needed, he said, was a new fundamental law of physics, the principle of relativity, according to which the laws of physical phenomena.
And yeah, we don't have that. Einstein didn't come up with it. Einstein came up with a postulate. The speed of light is a constant. He just said that. He just pronounced it. He never reasoned it.
Should be the same, whether for an observer fixed or for an observer carried along in a
Well,
uniform
that's the conclusion that we need to come to.
movement of translation. In other words, as Galileo had suggested, one state of uniform motion is as good as any other. After all, this idea was the basis of.
If Einstein ever said that he never heard of the Michelson-Morley experiment, that I don't see how that's possible. I mean, everyone was responding to this experiment. It's really weird that he should say that.
Of Galileo's reasoning and the law of inertia almost 300 years earlier.
I mean, that experiment was so baffling. How could you not hear of it? I guess, but why would he lie? He could have easily said, this is experimentally verified. Let's just start from that. He just started from that for no reason. Why? Why would you start from the speed of light as a constant for all observers, all inertial? Why would you say that? It's so bizarre.
But Poincaré was suggesting that the idea of Galilean relativity should be generalized to include all physical phenomena, including light. For example, an
all physical phenomenon, I wouldn't say including light, I would say including mass.
observer could not determine whether he was in motion by measuring the speed of light, since that speed is the same for all observers. And that meant age-old notions about time and space had to change. And though Poincaré himself shied away from examining the consequences, Lorentz developed the equations needed to show precisely how much rulers would have to
Falling asleep, oh my god.
all physical phenomena, including light. For example, an observer could not determine whether he was in motion by measuring the speed of light, since that speed
This is Einstein's postulate. An observer cannot determine their own speed. It doesn't mean anything. Which, if you assume ether, you can explain that within wave mechanics, within wave theory. I think we're able to explain time dilation. Length contraction, I would have to see, and why the mass. I don't want to say the mass needs to change. That's useless. I need to have a first principles reason why the mass increases. How could the mass increase? Well, the mass is just, what is mass? So the mass is just an illusion. It's just a bouncing back and forth. But what is causing the mass to increase? So as I'm moving faster and faster through a medium, why is my mass increasing? Why is my mass increasing? Why? It's like the Higgs mechanism. Things need to bounce faster and faster and faster as the mass is, as the speed is. I don't know.
is the same for all observers. And that meant age-old notions about time and space had to change. And though Poincaré himself shied away from examining the concept.
Let me check my schedule for tomorrow. I think I have something scheduled for tomorrow. Let me check. So tomorrow, yeah, tomorrow morning we gotta take care of that. All right, fine.
Consequences. Lorentz developed the equations needed to show precisely how much rulers would have to contract and clocks would have to slow down when they were in motion.
But no change in mass.
The essence of his reasoning can be seen with the aid of the simplest possible clock. Two mirrors a fixed distance apart.
This is incorrect. There's no. I mean, he's assuming. It's so weird. I mean, he has such a terrible clock with the ping pong. That is such a terrible thought experiment.
With a light beam bouncing back and forth between them. Each bounce of the beam is a tick or a tock of the timepiece. To Henry, his clock is stationary and altogether ordinary. But for Albert, that clock is moving. And between tick and tock, he sees the light beam trace a diagonal path. It means it's traveling along.
But why would a ping pong move at a constant rate? That doesn't make any sense.
But the speed of light is the same for all observers. So the light.
Why? That's because it's a wave. And everyone is observing the same media. And everyone so everyone is not moving. No one can move. Only the clock. See, this is confusing. So if you compare it to water, you cannot move with the boat through. You have to move only with the clock through. You cannot have anything but a clock. So the clock, if the clock moves, so if I'm observing you, then and I'm moving through the ether, through the water, then my clock is ticking slower. And let's say I'm moving through, and I'm watching waves waving away from me. So as I'm moving faster and faster, the waves are moving slower and slower away from me, but the clock is ticking slower and slower, so it looks like the same speed. But something would happen. There would be a Doppler effect. As I'm moving through space, there has to be a Doppler effect. That's why there has to be length contraction. But no, length contraction is both ways, both forwards and backwards. So, because all the way, I would have to notice the waves piling up in front of me into speed of sound. What do you call it? When you break through the barrier, the noise that it makes, the sound, the speed of sound, that clap that you hear. So why would I see? So I need to see the waves moving away from me at the same rate. So if my internal clock is moving slower, I would see them. But the waves moving away from me towards the back, so the waves moving in front of me are moving slower and slower. But what about the waves moving away from me towards the back? They're actually moving too fast. So if my clock, then I should see them moving way too fast. So how does that work? Oh my. So hi, what's up? Yeah, what's up,
I'm doing
Nidal?
pretty well. What about you?
I'm okay. I'm recording something, but yeah. How was your day?
I it was awful, like usual, because
Why?
I spend a lot of my time at
What?
home doing
Why?
nothing.
What?
It's in front of the PC because I have nothing to do outside. That's why I'm sitting here.
Wait, what are you doing all day?
N- Basically nothing. Scrolling in Twitter, what's so called now X, and watching some videos on YouTube and having I had conversations with some people in the politics server. That's all
Why don't you
I've
create?
I've done.
Okay, listen. Why don't you create a YouTube channel and start making content?
I thought about it, but I need uh, some gears for it
What do
to
you
be prepared,
What do you mean
to
gear?
be well prepared for the streams.
What do you mean gears?
Like the tools of streaming. No, no, I'm
What?
not uh, talking about the OBS. I don't mean OBS in this case, but I mean the webcam and
No, you don't need a webcam. You don't need to show your face to make content.
yeah, but no, 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 but it's
What?
you know the difference between you're showing your face in the live streams
You don't have
and
to show. No one
you're
wants to
not.
see your face.
It's a
You're not a girl.
huge,
You don't have to
it's
show
a
your face.
vast
You're a
difference.
guy.
Yeah,
Okay. Anyway,
I okay, Mrs. Safe.
what? So, like,
No,
why don't
I'm
you?
feeling so drained
What?
at this moment.
What?
I'm feeling so fucking drained at this moment. I'm feeling so fucking tired, exhausted.
Okay. So why
I
don't
need to take a rest because it's 6 p.m. in my time zone,
you?
and I woke up so early today,
Okay.
early morning.
And why don't
Yeah.
you like try and come and do a show with me tomorrow morning? Like as soon as you wake up, as soon as you're available, let me know, and we'll do something. We'll talk.
Oh, by the way, I played a game called Farmer's Valley.
I don't play games. I don't know anything about games.
No, it's on Discord activities.
I don't do that. I find that boring. I don't do activities. I'm just trying to figure.
No, no, it's for you, but for me, it's interesting.
That's good. But
Great.
tell me about it
So,
tomorrow.
okay, I catch you later.
Yeah, man.
By the way, I haven't played League of Legends today.
I don't know what that is.
That's the best thing ever I've ever done today.
Okay, I'd rather kill myself than play a game.
Thank you.
Yeah, enjoy.
Take care.
See you
Take care
tomorrow,
of
man.
yourself.
All right.
Bye.
Okay, see you. Bye.
See you again. See you again soon. Bye.
Yeah, man. Bye.
Bye.
Bye bye. All right, let's continue. Share this tab.
It must take a longer time to travel the longer distance. Therefore, Albert believes the moving clock runs slow. But how slow?
The relativity of time is derived from the right triangle formed by the distances traveled. The Pythagorean theorem shows that the path of the moving light is longer than the distance between mirrors. By the factor 1 over the square root of 1 minus v squared over c squared. This factor occurs so often in relativity that it is given its own symbol, the Greek letter gamma.
So to an observer at rest, a moving light clock seems to be running too slowly, by the factor gamma. A ruler, or anything else in motion, also seems contracted by that same factor, and it's called the Fitzgerald contraction.
Fitzgerald contraction?
For speeds much less than the speed of light, gamma isn't very large. For example, the Earth in its headlong dash around the sun, is shortened by no more than the length of one blade of grass. As for speed on the Earth, while Lorentz was busy developing his theory, the steam locomotive barrier of 100 miles per hour was broken. At that speed, the entire train is shortened by less than the width of one atom of the paint on its engine. And Lorentz himself didn't move slowly. He was the international physicist. Young physicists from around the world attended his lectures at the University of Leiden in the Netherlands, where he'd been a professor for a quarter of a century. Among those who came to Leiden was Albert Einstein. Over the years, Lorentz would have an enormous professional and personal influence on Einstein. Just before his death,
So they had a relationship, but everything Lorentz said was about Michelson-Morely, and Einstein never heard of Michelson-Morely. That's bizarre.
Einstein said, "I have admired and loved Lorentz perhaps more than anyone else I have ever known." But it was Lorentz's work as a theoretical physicist that went beyond his privileged circle of friends and traveled freely through time and space. Knowing he was on the right track, Lorentz pursued the consequences as far as he could. If moving things appear shorter and moving clocks run slower, then how can two people, moving in relation to each other, agree on a consistent description of where and when some event happened? To answer that, what's needed is a set of equations to replace the old Galilean transformations.
If you just think about moving through water, it's trivial. Nothing. I mean, there's no length contraction for water, and still they agree on everything. Why do you need to have length contraction? Why do you need to have length contraction? Do you really need to have length contraction? I mean, according to wave theory, you don't need to have wave length contraction.
These equations weren't hard to find, but some of their implications were hard to believe.
In Galilean relativity, the position of a point, x prime, in a moving frame is related to its coordinate in a fixed frame by x minus vt. Lorentz found that for the new relativity, this must be multiplied by the factor gamma. That's the equation along the direction of motion. In directions perpendicular to the motion, distances are the same in both frames.
And as for time, although clocks can be synchronized in any one frame, their readings in another frame may depend on where they are.
The time in the moving frame is gamma times the quantity t minus vx over c squared.
Together, these equations are the Lorentz transformation.
All right. So the first one is length contraction. The last one is time dilation. Why do you get length contraction? And why is it called Lorentz transformation? So Lorentz already derived it?
They express the mathematical essence of the special theory of relativity. The Lorentz transformation slows time and contracts distances in a moving frame, no matter which frame is taken to be moving. The observer in the moving frame thinks he's at rest, and that the other frame is really moving. But these equations do more than that. They actually join time and space together. When an event occurred has no meaning without saying where it occurred. (1904), the Netherlands. Lorentz publishes the definitive version of his electron theory. It contains
So this is 1904. Okay.
the essential equations of the theory of relativity. But Albert Einstein has not yet been heard from, which has caused some to say that history has given him more credit than he deserved. 1905, Bern, Switzerland. Einstein, a young physics student supporting himself as a patent clerk, finds himself disturbed by seeming inconsistencies at the very core of physics. Can inertia and the laws of mechanics be made consistent with Maxwell's theory of optics and electromagnetism? Einstein decides that they must, even if that means giving up not only the ether, but the traditional meanings of time and space. He sets forth two fundamental postulates. The first is Poincaré's relativity principle. The laws of physics are the same for all inertial frames.
So he just took Poincaré. Okay, so he didn't come up with this notion. He just said, okay, let's assume Poincaré. Just let's assume it.
His second postulate states that the speed of light is the same for all observers. He simply assumes the phenomenon that Lorentz has been struggling to explain. From these two postulates alone,
He just assumes the phenomenon that Lorentz tried to explain it because of Michelson-Morely, and Einstein never heard of Michelson-Morely. Not possible.
Einstein deduces exactly the same equations Lorentz discovered earlier, but now they have a very different meaning. The fundamental concepts of space and time have become intertwined. The essence of the idea can be understood by visualizing time as if it were another dimension. Albert, standing still in space, flows through time, so that a vertical line represents a fixed point, x equals 0, in his reference.
This is nonsense. There's nothing special. What are you talking about? There's nothing special about space and time according to special relativity. Time is just an artifact of moving through the ether. It's so technical. It's so mechanical. What are you talking? There's no fourth dimension. What are you talking about?
Frame at different times. while a horizontal cross-section represents simultaneous times in different places.
That's utter nonsense. That's magical thinking.
On the other hand, someone in motion, Galileo for example, traces an oblique path.
You can draw the same diagrams for objects moving, for clocks ticking through water
So while what Albert thinks of as a fixed point makes a vertical
and moving relative to each other.
line, Galileo's idea of nothing happening appears as a tilted line at x prime equals 0, or anywhere else in his frame. But of course, if Galileo had drawn the picture, his line for standing still would be vertical, and Albert's would be tilted backward. The same idea can be used to show the relativity of time. When Henry and Albert observe the same expanding light sphere, it reaches their detectors at definite points in time and space. These are called events. Meanwhile, the light itself traces out a cone. To Albert, events on the horizontal cross-section are simultaneous. For him, one of Henry's detectors flashes first, then both of his own flash simultaneously, and finally, Henry's other detector flashes. So he thinks these two events are simultaneous, but Henry thinks these two events are simultaneous. So not only are Henry's lines of constant position tilted, but so are his lines of simultaneous time. For Henry, simultaneous events take place everywhere on a tilted cross-section. So he thinks one of Albert's signals goes first, then both of his, then Albert's other signal. Of course, if Henry were drawing the picture, he would draw his lines of constant place and constant time perpendicular to each other. Amazingly, that wouldn't change the light cone at all. This way of looking at things is called a space-time diagram, and many of the strange effects of relativity can be visualized this way. For example, Albert thinks that Henry's ruler isn't quite a
This relativity, notice that they only mention time dilation. They're not talking about, when they do space-time diagrams, they never do anything about length contraction.
meter long. While Henry, seeing Albert speed by, thinks Albert's ruler is shorter.
Can you simply explain? I'm wondering if we can do the math to prove the Michelson-Morley experiment simply with time dilation, without length contraction. Will time dilation alone explain it? All right, that's what we should do tomorrow. Let's make a note. So let's write in the notes for this show, the next show. Next. Can we use time dilation alone to show Michaelson-Morley experiment? Just to show it, just to reproduce it, just to predict it, or explain it. So can we use time dilation alone without, what I mean is without length contraction, without length contraction to explain Michelson, we should say the Michelson, I don't like saying the, I'd rather say Michelson and Morley's. Should you say whatever? Everyone says the Michelson-Morley experiments. That's next episode or next show. Next show, yeah, it's our show. We're doing a research show. Oops, where are we? We're here. Belay.
On the space-time diagram, Albert measures lengths on his space axis, where Henry's ruler is shorter. But on Henry's axis, the situation is reversed, and Albert's ruler is shorter.
Oh, so they do derive length contraction from this, but they need to explain it. This needs to be explained. Like in water waves, you don't expect to get length contraction. In our universe, you get length contraction maybe because of the electron.
And what about the mystery of the clocks? How can each think the other's clock is slow? On the space-time diagram, just follow the bouncing light beams. On Albert's time axis, Henry's ticks are farther apart than his own. But on Henry's time axis, Albert's sticks are farther apart, no matter how he looks at it. Actually, there's more than one way to look at the Lorentz transformation itself. While it was first derived by Lorentz, Einstein arrived at the same equations, but from a completely different direction. Lorentz used the equations to explain the Michelson-Morley experiment, while Einstein's goal was to establish relativity as a fundamental and universal principle for all of physics. For Lorentz, the constant speed of light for all observers.
Einstein just assumed weird assumptions out of thin air, especially the constant speed of light. Why would you assume the constant speed of light? Love of my life. I love this chick so much. Oh my god, I'm getting so many hearts. Oh my god, I'm getting so many hearts. She's so beautiful. So this is the chick that I met at the party last week. So beautiful. Oh my god. Can't believe I'm getting hearts from the most beautiful chick. I go to a party, I see the most beautiful chick, walk up to her and just ask her if she's interested. And she didn't say no. She hasn't said no yet. So we're going out for a second date, hopefully this week. This is so cool.
Was a mere appearance. For Einstein, this constant speed was a principle from which all else should be derived. Lorentz was perhaps the last great classical physicist, but the equations that bear his name are at the heart of relativity and the future it created.
In any case, there are two completely independent histories of the theory of relativity. One of them goes this way. There was the ether theory, and in the Michaelson...
This is so weird. I mean, Einstein is... He's not making any sense. The story he's telling, he's breaking from logic as far as the story is concerned. Like, why would you just assume a constant speed of light without knowing about Michelson and Morley, where you were in contact with Lorentz? I mean, you quoted Lorentz on your paper, you referenced Lorentz on your paper, and Lorentz was working tirelessly to deal with Michelson and Morley. Yet you'd never heard of Michelson. What's going on here? One of them goes this way. There was the ether theory, and in the
Morley experiment and other experiments failed to detect its existence.
We don't have enough information. Where is the journalist who went and interviewed Einstein and asked him, what the heck is going on? Could you give us the timeline of what's going on here? Things don't follow.
And then Poincaré and Lorentz, with great difficulty, produced the formulas that were necessary to explain the results of those experiments. And then, completely separately and independently, young Albert Einstein was worried about a deep problem having to do with the nature of light and electricity, and he decided that this...
What do you mean the nature of light? What do you mean the nature of light? He just assumed a constant speed of light. Why would you ever assume that? Why would you assume that? And he never explained why he's assuming that.
This was the way the world had to work. And he came up with
What do you mean this is the way the world had to work? Well, why would the world have to work like this?
exactly the same theory, but with a far, far deeper understanding of what it meant.
No, there was no far deeper understanding. He just took it and ran with it, and they took it and tried to explain it. He didn't try to explain it. He just looked at the implications. He never explained it. We still don't have an explanation. Why is the speed of light constant?
So, it's possible to say that Einstein made only minor contributions to the theory of relativity, just as it's possible to say that Copernicus did nothing but a trivial mathematical transformation of coordinates. But to say that...
That's what I'm doing. I'm just doing a trivial transformation of how to view all these theories with the ether. When you use the ether, when you assume the ether, everything makes much more sense. Special, general, and quantum physics fit together perfectly. The ether is the unified field. It unifies everything naturally.
That ignores in the most profound possible way the real history of both of those subjects. That Einstein made only minor contributions to the theory of relativity, just as it's possible to say that Copernicus did nothing but a trivial mathematical transformation of coordinates. But to say that ignores in the most profound possible way the real history of both of those subjects. We'll go on with our discussion of the theory of relativity next time.
Oh my God. Oh my God. Oh my God. Doctor. Everyone is a doctor. Computer animation, doctor. The doctors did the computer animations because you need to know special relativity to do to do the actual transformations. Everything needs to be, you need to understand physics when you, and here is academic consultant is Goodstein, who's I guess the narrator, the teacher. Physics demonstrations, researcher. So there on top of this, there's a researcher. This is interesting. So Caltech produced this amazing series. Wow. Caltech, Cambridge, NASA, Henry Ford Museum, LA Trains. Oh, LA Trains. Caltech. Okay, so this was
Annenberg Media.
Annenberg Media. Fascinating. This is like high production quality for 1,000 years ago.
And visit us at www.learner.org.
Oh, they used to always, so there was already a website. This must be from probably, I guess, 20 years ago. This is 20 years old? No, this must be more than that. I would say this is 40 years ago, 50 years ago. 1985. Yeah, okay. So this is 1985 production. So they didn't have a website in 1985, not even in 1995. Maybe in 2005 they added the website information. So this is 1985. So 85, that's 15 years plus now we're in 25 almost. So it's 40 years ago. Yeah, right? 25. Yeah, about 40 years ago. Yeah, just as I suspected approximately. Fascinating. Okay, ladies and gentlemen, this was interesting. Okay, we'll continue. We said what we're doing next tomorrow. So tomorrow we're doing, next show is can we use time dilation alone to explain the Michelson-Morley experiment? Why do we need length contraction? Do we need length contraction? Shouldn't time dilation alone do the job? And is there really length contraction? Has length contraction ever been proved? Has anyone done an experiment proving length contraction? Okay, let's just write experiment. I think this is not true. My intuition is you don't need that. Time dilation should be enough. Yes, we see this with atmospheric muons. That's time dilation should be enough to explain atmospheric muons. For example, these are subatomic particles that fall in from the atmosphere towards Earth, and we detect them here on the ground. The thing is, their lifespan is too short to explain, why shouldn't time dilation be enough? It's on the experimental proofs of relativistic length contraction. Calculation presented. I don't care. This is not an experiment. This is not an experiment. This is a phenomenon that we've noticed. This is not an experiment that we set up, unless, oh, whatever. It's okay. Length contraction experiment has ever been an experiment verification of length. How would you verify it? Because your ruler is gonna shrink. It's a new theory that explains quite a bit. I don't know. Time dilation, yeah, but why do you need length contraction? Shouldn't time? Why do you need length contraction? Why do you need length contraction? You don't get length contraction from wave theory. Whereas we said we started watching the video. History. History. That's so funny. My own channel is in history. So we saw a video from dialect. Where's the dialect video? Where is the dialect? This is it. The dialect video. Let's look at it.
Imagine that you're going to build yourself a pair of clocks. But these won't be any old clocks. Rather, special clocks, which tick using sound waves. The concept is simple. At one end of the clock, you'd have a detector waiting to receive a particular sound wave, which, upon its arrival, would cause that detector to register a tick of its clock. This detector would then reflect or re-emit that sound wave back towards a second detector at the other end of the clock, which would in turn receive it, register another tick, and once more re-emit the wave back. Thus, with a sound wave continually passing between the two detectors, you'd have constructed a viable instrument for measuring the passage of time.
This is an incorrect animation because each wavefront should register one tick. No, unless you're going to send in only one wavefront. So you're supposed to send one wavefront, register it, and then send back one wavefront. If you're sending multiples, then then you should register each one and then send back the multiples. That's fine, but it's called duplex. That means they're going back forth and going back, have like a overlapping. And the other way, if you're only sending one and then the other, I think that's called half duplex. Full duplex means you're sending the signal this way while receiving signals. You're sending and receiving simultaneously. So is this full duplex equipment? Wait, what's going on? What happened? Thought somebody walked into the room. Maybe somebody walked in and out. Oh no, I didn't mean to share this. Jesus, what did I mean to share? We were watching dialect. There we go. Anyway, the animation, they didn't think through the animation. Once I asked him a question about his animation, about the black hole and stuff, and he said, yeah, we're not too worried about specifics. It's fine. It's not healthy, in my experience, to be inaccurate when you're doing animations. Like, I try to be as accurate as I can when I do animations, when I draw diagrams. Anyway.
Now you make the following claim. Using these clocks, you can prove...
Unless you say, okay, I'm going to send you 2, 3, 4 is considered to be a signal. So you can actually encode a signal. You can actually do like 0, 1, 0. I mean, you can actually send data on. You can actually encrypt the data that you're sending. This could be really, really interesting, but it's not important. Immaterial.
Prove that time is relative. To do this, you keep one clock ticking.
But no length contraction. Let me see. Has anyone mentioned length contraction? Let me scroll through a little bit so we can do a search. Length. There's 4 lengths. 2. I don't see it. Oh, it's on the side. Contraction. Yeah, it's one video, the other video, I guess. There is no discussion of length contraction in the comment section. Let's add more comments. There's a lot of comments. Okay. Still nothing. Still only 2. All right. All right. Let's continue.
Ticking at the same location and proceed to fly the other clock around the world. Ideally, this flown clock should be as aerodynamic as possible. Additionally, it should not be enclosed in any structure, but rather exposed to the open. Now, when the clocks are reunited, you find that less time has elapsed on the traveling clock than on the stationary one. What caused
Yeah, that's literally time dilation.
this discrepancy? Well,
This proves that space must flow through us right now.
the answer is simple. Sound waves travel through the medium of air, and do so always at the same speed.
This is so beautiful. This completely disproves everything about special relativity, the foundations. I mean, just the foundation. I mean, Einstein just started from an assumption, but you don't need the assumption. You can start from first principles like this.
The speed of sound.
Wow, I just want to look again at all the emojis that she sent me. Oh my god. Oh my god, she's so amazing. Oh my god, she's so amazing. Oh my god. Oh my god. Oh my god, this is so exciting. So exciting. Da 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 da.
Regardless of the speed of the source which emitted them.
Wait, what's this? Pedant corner? Yes, we know sound travels through many mediums and its speed is variable depending on the density of that medium. For this video, only sound waves traveling in air of uniform temperature are considered.
This means a sound clock in motion will function essentially.
I guess pedant just means that like you're a stickler. Pedantic, I guess.
Differently from a sound clock which is at rest. To see this, let's label the speed of sound as c and observe how the ticking of a sound clock at rest compares
It's so funny, that's what I did. I labeled the speed of sound C.
to one in motion. If the distance between the detectors is d, then for a clock at rest with respect to the air, the time it takes a sound wave to travel that distance will be d over c. But if the clock is in motion, the distance that the sound wave has to travel between detectors now becomes greater
Perfect.
than d, meaning it takes a longer amount of time for the wave to travel that distance, and thus a longer time for the moving clock to tick. This relationship between ticks on the two clocks can be easily quantified via some simple trigonometry. First, for a clock.
What's incredible is that as we move through the ether, we don't feel it. It's like even though the waves are always waving they're always delayed. They're always waving like this. They're always waving to the other mirror, but the other mirror is gone by. But this doesn't have any impact on us. That is weird. Like you'd expect the motion to rattle the mechanics. The waves are now they it's like shouldn't they be offset?
Clock moving at velocity v, let's label the distance which the sound wave has to travel between detectors as d prime. Now, the at-rest clock ticks.
I don't care about this that much. I mean, the question is, they don't have length contraction, obviously. There's no length contraction. The question is, why did Lorentz get length contraction? That is my question. So let's go here and ask Lorentz length contraction from Maxwell. I think there was a dialect episode about that, but they didn't go into the theory. They literally said we're not going to go into that. There is the length contraction, but that's not from Maxwell. So Lorentz, and he didn't say, he just said he has an intuition. So Lorentz length contraction is a fundamental constant in special relativity, describing how objects appear shorter to an observer when in motion relative to them. No, it's not about appearing. It's just about appearance. If it's just about appearance, then we could get that. Yeah, you would get that actually with sonar. So if in our thought experiment with water, so maybe they do have it. Maybe dialect will show length contraction. Do they have length contraction? Hearing, there's no length contraction. Twin paradox, dynamic relativity. This is good. So they're able to resolve the twin paradox much easier. The clock paradox, deriving gamma, it's about uncertainty. But what about length contraction? Length contraction? But what about length contraction? But what about length contraction? Right? But what about length contraction? Wait, I'm not sharing this yet. Let me share. So this is what I just typed in this message. So this is in dialect. But there's no length. I don't think they're doing length contraction in this episode. Now going back to looking for no, not this. What did I want to look? This one. Lorentz length contraction from Maxwell. This is not from Maxwell, is it? And by the way, this says it appears. So my question is, if we go back to, I think, if you, right, because we use our eyes to see length, and we would see length contraction. But the question is, the point is that Maxwell claimed that the arm would become contracted, but would it? You need the arm to become contracted, don't you? Because time dilation doesn't help you in Michelson-Morley experiment. Time dilation doesn't help you. It's one beam split in two and then reforms into one beam. There's no different clocks. There's no clocks here. There's no time dilation. There's no clocks. It's straightforward a beam. So if it's so the question is, can they reproduce the Michelson-Morley experiment? So can you reproduce the why don't you reproduce the Michelson-Morley experiment? Wouldn't you need length contraction? Can you let me share the tab. Can you let me move my mouse. Can you reproduce the Michaelson-Morley experiment? That's the first question. According to Lorentz, who was the guy before Lorentz that said no, his intuition, it's going to contract? But Lorentz agreed. Shouldn't you need Lorentz length contraction to explain the null result? Can you reproduce the Michelson-Morley experiment? Meaning with the sound using your sound clock. Shouldn't you need the Lorentz length contraction to explain the null result? The experiments null results. Another day, another night, la 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 la, la 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 la. So this guy's doing his PhD in physics. I'm going to say special relativity is not mysterious. It is counterintuitive but well understood. All right. The twin paradox has been solved for a long time and it is well understood in the scientific community. Just because some YouTuber, wow, this guy's upset, can't explain it well, it doesn't mean it is not solved. All right. The ether approach to special relativity was disproven by the Michaelson-Morely experiment a long time ago. Yeah, of course, of course. Yeah, sure. Einstein might have something to say about that, though. 1920 lecture. Special relativity is the foundation for general relativity and quantum field theory, the two most successful theories in physics. So any modification of special relativity must figure out how to still predict particle physics. Are you out of your mind? Just the opposite. The standard model, oh my God, black holes. Yeah, of course. Yeah. The expansion of the universe. Yeah. The similarities between sound and light are well understood by the fact that both satisfy a wave equation, and wave equations have Lorentz symmetry. These are good words. What is Lorentz symmetry? Thus transforming according to the gamma factor. But the similarities end there, since light is a wave of electromagnetic field, which has been proven to propagate through empty space many times. Yeah, okay. The Michelson-Morley experiment was for a stationary ether. If it was in motion, like the river model video describes, they would not have detected the ether wind. What? If the Earth goes around the Sun at terminal velocity, then there should still be some wind. But if all the ether in the solar system was twisting like a whirlpool, that might not be the case. I disagree. Ether is completely disproven. I'm going to need a bit more than your word on that. People are actually arguing in the comment section. You are lucky then. He's talking about this PhD? No. Who is Capitano 3483? Oh my God, we have to remember. Is anyone responding to Capitano? Oh my God. So at Mach 1, a clock stops registering time completely. Yep. But assume, anyway, these are really interesting comments. Any methods we can devise to measure time ultimately depend on the propagation of electromagnetic waves. Yes, even mechanical clocks. If there is an absolute time, we cannot observe it. Yeah. Any clock we can come up with will experience time dilation. Exactly. Perfect. Perfectly said. That doesn't really make sense. You're an idiot. Oh my God. You analyzed what happens when the sound clock is ticking perpendicular to the direction of motion, but what happens when it's ticking parallel? I don't think there's a difference because it's going to slow down. In one way, it's going to speed up. In the other way, it's going to slow down, but it's going to slow down more than it speeds up. For one tick of time, it takes d over c minus v, and for the other, it will take d over v plus z. For the total, it's this. This gives you a time dilation factor of this with no square root. Notice that's very different from the transverse case. Wow, they actually went through the math. Was the difference between parallel and perpendicular ticking that the Michaelson-Morley experiment was looking for and didn't find for, there is no difference. That's why those papers describe this as a pedagogical tool. The luminiferous ether was ruled out by experiment more than 100 years ago. Note also that for sound, the Doppler shift generated when the source is moving is different than what's seen when the observer is moving. No, okay, I don't know anything about the Doppler. Okay, yeah, they made a good point. Time and space are not attributes of the universe, they are attributes of our knowledge of the universe. That's good. However, as your medium's density and other flow characteristics change, your sound, of course, your calculation. That's good. That's You've missed a very crucial point on light clocks, which unfortunately is rarely, if ever, mentioned, namely the fact that their use as time reference is only justified by first accepting the postulate that the speed of light is independent of the observer. Okay, I don't know what to say. So I'm looking for the Lorentz. We're gonna do this tomorrow. The Lorentz length contraction, and is it real? Because according to, so the question is, do we need anything more than time dilation? Let's look it up. So Michelson-Morley experiment, just add time dilation. If you add time dilation, do you fix it? The Michelson-Morley experiment 1887 was groundbreaking test of the luminiferous ether theory, which posits. But where is the discussion of time dilation? Time dilation connection. Although the book did not directly measure time dilation, its outcome has a crucial connection to the concept. The experiment's null result implies that time is relative and depends on the observer's frame of reference. Yeah, because right. So one arm moves relative to the ether. So that arm slows down, but the arm doesn't do anything. The arm doesn't do anything. And we already took into consideration the slowing down and speeding up, or the speeding up and slowing down of the arm of the wave through the arm. So how does time dilation help the Michelson-Morley experiment? I don't see how time dilation can help. So you have to have length contraction. So time dilation comes out of Michelson-Morley experiment, but I don't need time dilation to come out of it. I could have predicted it from wave theory, from wave mechanics. So that's not an issue. The question is, has the arm actually contracted? Do you need the arm to actually contract? So the answer is, of course you need the arm. Then how would you reproduce this experiment? So you can never reproduce this experiment with water waves. With water waves, you're never going to get a null result. Is that what you're saying? I'm never going to get a null result. I'll always get an interference with water waves? How's that possible? What's going on? So I'm always going to get, oh my God. So I'm always going to get, so I cannot reproduce the Michelson-Morley experiment with any type of wave except for light, because light changes the shape of the electron. This is bizarre. That's the only way we can fix the Michelson-Morley experiment. We have to have length contraction. We cannot get away from it. Implication of time dilation. Time dilation cannot fix it. Time dilation comes out of it. Time dilation comes out of it. The experiment's outcome laid the foundation for Einstein. I don't care. Michelson-Morley it's so hot. Einstein. Oh my God, this is so confusing. Michelson-Morley experiment did not directly measure time dilation, but its outcome has crucial connection to the concept as it implies the relativity of time and sets the stage of. Both clocks were ticking slower. The clock ticking that the flow is through it, and the clock that the flow is perpendicular to it. Anyway, the clock is going to tick slower, but you're going to get interference. The only way you're not getting interference is with length contraction. And you have to explain, so there has to be a physical length contraction. So the ether, by wading through the ether, you have to change your shape. You physically have to become oblong, blah, blah, blah. So how does Einstein explain that if it's in a vacuum? Because in Einstein, it's just, how does Einstein then explain Michelson-Morley? How do you explain? So you're saying it's not really contracting, then if it's not, wait a minute. How does Einstein explain Michelson-Morley? Length contraction? Length contraction is only to an observer. There's no observer in Michelson-Morley. Michelson-Morley, there's no observer. There's an observer? It's just an interference. Has Einstein ever explained Michelson-Morley? Is this why he said he never heard about it? Because he didn't want to, he knew he couldn't fix it? He can't fix? Einstein can't explain Michelson-Morley? Because his time dilation is real, but his length contraction is only in the eyes of the observer. It's not a physical phenomenon, according to Einstein. Wait a minute. Hold on, let me ask dialect. What is going on? So Einstein cannot explain the Michelson-Morley experiment? Has anyone ever explained? Oh, that's why they don't want to have the ether. It doesn't matter. It doesn't matter. The length contraction is only relative to the observer. Where is the observer? How can... Has anyone ever explained the Michelson-Morley experiment? Oh, they just say there is no ether. There's just no ether. Oh my God. Oh my God, that's what they're saying. Oh my God. That's why they got rid of the ether. Oh my God. We have to catch them on this. There has to be a way to catch them. There has to be a way to catch them on this. So they said there is no ether because they cannot deal with the length contraction. But if Maxwell predicts length contraction, then they are in trouble. Wait a minute. But Maxwell never predicted length contraction. What is this Lorentz length contraction? What is going on here? That's why they rejected Lorentz. There is no length contraction. He never proved it. Lorentz length contraction is a fundamental concept, especially describing, I don't care. That's not from Maxwell. From Maxwell. Give it to me from Maxwell. This formula indicates that as an object approaches the speed of light, its length contraction becomes more pronounced. I don't care. Lorentz length contraction is a constant transformation of electromagnetic fields between reference frames. That's not a real phenomenon. If you believe in the ether, you have to physically contract. Hold on. If you actually contract, if the contraction is real, Relative to what? Oh my God. How are we going to disprove them? There's got to be a way. Length contraction. Length contraction is a phenomenon that a moving object's length measured to be shorter than its proper. There's got to be a way we can prove the ether. What's this? Derivation of length contraction from Lorentz transformation transforms. No, I want to know about deriving it from Maxwell. They said that you can derive it from Maxwell. That means it's real. Are Maxwell equations relativistic? I don't care. Time dilation, length contraction. Okay, it's too cold. Oh my God, this is out of control. Oh my God. Help me, God. Help me, God. Oh my God, this is so difficult. This cannot be any more confusing. I guarantee it. Okay. Dialect made a video. They said it's caused by Maxwell. All right, let's go. Let's go, Maxwell. Where are you, Maxwell? Let's go. So there is a YouTube video. Let's go to the YouTube videos. Not this. Okay, we're done asking questions here. I need to keep this open. So let's open another one and share this one. Atoms to quarks, the mechanical universe. Oh my God. Let's go. All right. So, I think it was dialect. Lorentz length contraction. Relativistic wave mechanics. How superposition causes length contraction. Superposition. Really explains the principle of relativity. They have the craziest videos.
So everything then turns on the following question. Can the equation for the pancake... The phenomenon of length contraction is an indispensable element of the theory of relativity.
I'm thinking, if I'm moving relative to the contraption, the interferometer, the Michelson-Morely experiment. The Michelson-Morely experiment uses an interferometer. We shouldn't say their experiment. We should say the Michelson, it's his interferometer. It's their experiment, but it's his interferometer, no?
But is the contraction of physical objects even real?
Yeah, that's the question. Is the contraction real? So if the ether exists, we actually need the contraction to be real. So Einstein's contraction is not real. It's a relative effect, it's a relativistic effect. The clock ticking is real, but according to Einstein, it's not real either. It's a relativistic effect. It's relative too. But according to the ether theory, these are real effects. Things are really slowing down and things are really getting contracted. These are not relativistic. This is so amazing. How did Einstein manage to confuse everyone like this? How did he manage to confuse everyone like this and everyone bought it? Lock, stock, and barrel. Hook, line, and sinker. Whole cloth. They swallowed the whole thing. And they went bananas right after. And now we have to pick up the what do you call it? The broken pieces.
And if so, what actually causes it? The theory of special relativity is notoriously ambiguous on this subject. But we'll find that by drawing a
Yeah, Yeah, no one wants to hear that. Yeah, notoriously ambiguous. Yeah, they don't want to hear that. To them, it's clear. What are you talking about? It's resolved. It's all settled. To them, it's all settled science. You're just a YouTuber.
Little inspiration from other contemporary theories, we can begin to piece together a solution to one of the longest standing mysteries in modern physics.
Who is this guy?
Plus, uncover a whole lot more. This is Dialect with How Superposition Causes Length Contraction.
Yeah, but that's superposition. That's not Maxwell.
There's something almost magical that happens to the electric field of a point charge when it's set in uniform motion. No, it's not that the field lines become squished in towards the transverse direction, and as such the field ends up looking like a pancake, though this will become very important in a second. Rather, it's that these field lines actually wind up moving perfectly in step with the charge. Think about it for a moment. This is totally bizarre. One of the core ideas of modern physics is that information can't travel faster than the speed of light. So how could the field lines of a charge know to become instantaneously translated along with that charge itself?
How's that possible? Isn't that a violation of the speed of light?
How does this field vector here, for instance, know how to always point towards the precise location of the charge, and with the appropriate magnitude, despite that information clearly needing time to travel from the charge to that field point? Indeed, one would rather expect a clear delay between a charge's movement through its electric field and the altering of that field itself. Something ultimately that should wind up looking like this. And although we do observe such delays when charges are accelerated, strangely, we don't observe them when charges are moving at uniform velocity. Instead, all we observe is just the perfectly co-moving pancake field. This strange fact is often cited as proof of the postulate of relativity. That is, the assertion that there is no physical difference between a frame at rest and a frame in uniform motion. Indeed, it's argued.
What do you mean? If I'm seeing it moving, then this is still a violation. What do you mean? This is a violation of the theory of relativity. What's going on? I don't need it to accelerate, and this can't be happening. If it's moving relative to me, I need time. I need there to be time between its motion until I see the motion. When I see it here, so all the vectors have already corrected for that. But what about a vector that's far? Let's say I'm close, but that vector is far. But by the time I see it, but how can I see a vector? What would it that? I guess there's test particle. I don't know.
Argued that if we transform into the moving charge's frame, we can treat both the charge and its field as being at rest. Therefore, the field and charge must always remain synchronized for any inertial movement. But there's a huge ambiguity in this argument, because there is an important physical difference between the frame of a charge at rest and the frame of a charge in uniform motion, which is precisely the aforementioned pancaking of its electric field.
Oh, so it does pancake. Oh my god. I never looked into this. I don't know anything about this. What time is it? Jesus Christ.
Indeed, it's this pancaking which is responsible for one of the most famous phenomena in all of relativity: the phenomenon of length contraction. To see why, simply place a charge in the moving field at a contracted distance of L times 1 over gamma out from the source along the line of motion, and calculate the force it would feel there. Turns out that force is the exact same as the force it would feel at a distance L out from a charge at rest. This is because the electric field of a moving charge gets reduced by a factor of 1 over gamma squared along the axis of movement, hence causing its pancake shape.
Why would the energy drop? The energy, wait, no, the energy rises. Why does the energy, is this because of E equals mc squared, that the mass rises? But this has nothing to do with mass, all right, so this is just the energy. Electric field equation, kq1 over r squared, this is the electric field.
And so to offset this shrinking, we must move the charge in closer
But why is this true?
by a factor of 1 over gamma.
So if we move it closer...
Doing this indeed, we see the 1 over gamma gets squared in the denominator of the inverse square portion of the modified electric field equation, and cancels with the 1 over gamma squared in its numerator, leaving simply the force the charge would feel at a distance L out if the field were at rest.
Yeah, I'm lost.
This here provides us the only physical explanation we could ever possibly need for length contraction, which is of course that intermolecular bonds are weakened by motion, and hence must be moved in closer to one another to retain their original configuration.
Why are they weakened by motion? Why would an electric field be weakened by motion? The energy goes up.
But still, this explanation leaves a number of unanswered questions. Why does the electric field get pancaked in the first place? And moreover, how is it that the moving field manages to stay synchronized with its charge? This is where most physicists and teachers simply throw up their hands and say, well, that's the magic of relativity. The
No way.
synchronization
That's Feynman. I don't like his definition of science.
occurs because uniformly moving frames are somehow the same physically as at-rest frames, with the exception of the field pancaking, which occurs because space itself is relative and somehow mysteriously contracts. But science is not magic, nor should it be reduced to it.
That's good. That is the most important understanding. Science is not magic. You have to understand everything mechanically.
And as we've explored in prior videos, there's actually no such thing as the contraction of space itself.
Good.
Lorentzian geometry is merely a descriptive convention that results from observers always choosing to calibrate the speed of light as being isotropic in their own inertial frames. Indeed, with appropriate synchronicity choices for our clocks, we can make Lorentzian invariance entirely vanish, and along with it, any contraction of space itself. However, the contraction of physical objects does not disappear with such synchronicity choices, meaning the phenomenon of length contraction must be regarded as entirely physical, and hence as having a causal source. So everything then turns on the following question.
So if I travel, the faster I travel, so according to relativity, the distance that I'm about to travel gets contracted. But that should not happen. It's just that my clock slows down, so I just feel like I traveled faster. and certain things I would experience that would make it would seem like things are getting the length is getting contracted.
Can the equation for the pancake field be derived without invoking any notion of relative space or time whatsoever, in some sort of mechanistic or classical manner?
Wow, that would be amazing. At least, so that's what's incredible. Dialect is speaking exactly in my language. Everything must be mechanistically explained.
Well, actually, yes. And in fact, this was how it was first done, way back in the 1880s by the English physicist Oliver Heaviside.
Never heard of him. What year? When? 1815, 1925.
Indeed, at the time, and in fact, this was how it was first done, way back in the 1880s by the English
1880.
physicist Oliver Heaviside.
1880, 18, this is right after the Civil War. So 1889 is the Michaelson-Morely experiment.
Indeed, at the time, he and other physicists
So he had a strange haircut.
derived this equation through a method that invoked something called the retarded potential. But at the time, the math behind these retarded potentials was complicated and obscure. And physicists didn't know nearly enough about our microscopic world to begin approaching any real interpretation of it.
Indeed, the first theory of retarded potentials, published in 1867, was rejected by Maxwell himself, who mistakenly believed it would lead to anisotropic forces and infinite acceleration. What is anisotropic?
Today, however, we understand our
Oh my god, I'm gonna die. My brain is fried. I gotta go to sleep. Are we here?
microscopic world much more completely, including the very central role played within it by wave mechanics. Indeed, if there's one thing that modern quantum field theory tells us, it's that light itself performs one of the most crucial tasks in our physical world, that of communicating the electromagnetic force. But what happens if we bequeath unto force all the additional phenomena of wave mechanics, but
1 second.
itself
No, I wanted to look at all the emojis that she sent me. So delicious. She's so delicious. Oh my god, she's so delicious. You've never seen such a beautiful creature in your life. Oh my god, she's so perfect. I have to eat her completely. Just eat her. Just eat her. He's my food. I need my nourishment. Oh my god. Oh my god. God, please help me. Oh my god. She's too much. I can feel that she was smiling when she got my message.
performs one of the most crucial tasks in our physical world, including the very. And physicists didn't know nearly enough about our microscopic world to begin approaching any real interpretation of it. Today, however, we understand our microscopic world much more completely, including the very central role played within it by wave mechanics.
Oh. Wave mechanics? Well, I guess there's wave mechanics at the quantum level.
Indeed, if there's one thing that modern quantum field theory tells us, it's that light itself performs one of the most crucial tasks in our physical world, that of communicating the electromagnetic force. But what happens if we bequeath unto.
So that's not a good diagram. I always complain when I see these diagrams. You have to remember that this is a sphere. That these are spheres. You could view them basically like sound waves, a little bit. But sound waves are compression, which are more like gravitational waves. These are a little different. So this is basically like when you throw your blanket over your bed, like when you make your bed in the morning and you throw the blanket and create waves through the blanket. So that's the wave going up and down, but it's a sphere. You see, this is a sphere, right? This is a cross section of a sphere. It's so difficult to imagine. This is the sphere. You can imagine the wavefront of the sphere is moving obviously with the wave. That's the wavefront of the sphere. The sphere is perpendicular to the blue. I don't know what to call this line. To the line of propagation. But it is a sphere. It's a sphere that all the molecules in over here are right now going up. All the molecules in this sphere are going up. But you would say, but how could that be in a sphere? Right. So it's not completely, but sort of. But it's a three-dimensional propagation of something, of information. So over here it looks like this, maybe a little, but if you draw another diagram, anyway, whatever. We got to find a simulation for Maxwell's equations in 3D. It's got to be there. Someone must have done it. It's so simple. It's so straightforward. I need to look into that. Anyway, okay. So what do you want to say? So this is the mediation of the electromagnetic force. Light mediates the electromagnetic force, or light is an electromagnetic wave. So what does it mediate? The electric force? No, that's not the electric force. What did he say?
Crucial tasks in our physical world. That of communicating the electromagnetic force.
Oh, the electromagnetic force. So light communicates the electromagnetic force somehow.
But what happens if we bequeath unto force all the additional phenomena of wave mechanics? Well, with a little pluck and insight, we can now do today what physicists 130 years ago could only conjecture about, and begin to account for the strange behavior.
That's not what electromagnetic waves look like. These are surface waves. Electromagnetic waves are 3D creatures. They are spheres. I don't know why they don't show it. Even like I would show it here. It showed a three-dimensional implication.
Little pluck and insight, we can now do today what physicists 130 years ago could only conjecture about, and begin to account for the strange behavior of the pancake field.
Oh my God, Jesus help me.
Let's imagine we have a basic point charge and we want to develop a model where the forces
So Q is a point charge.
due to this charge propagate outwards at a finite speed as waves through some sort of medium. For obvious reasons, we'll start by assuming this propagation occurs at the speed of light c.
Why would it propagate? It needs to be moving. So this charge is moving, right? Did he say that the point charge is moving? Otherwise, why is it creating
Let's
waves?
imagine we have a basic point charge and we want to develop a model where the forces due to this charge propagate outwards at a finite speed.
You got to say that it's moving. It's got to do something. It's got to accelerate. It's got to do something in order for waves to come out of it. Otherwise, there's just going to be a field without waves. What time is this? This is 8:47. Oh my God. 8:47. So at 8:47, the point particle, point charge particle, point charge particle can only make waves if it is accelerating. Right. Only if it's accelerating, it can create, relative to an observer. It doesn't have to be. It depends on if you believe in the what do you call it, in the ether or not. But just said it has to be. Oh, accelerating, you don't have to have Again, accelerating or moving, whatever, but the point charge particle can only make waves if it is accelerating. And you didn't mention that. The narrator did not mention that. Or why did the narrator? Oh my God. Why did the narrator not mention that? Jesus.
as waves through some sort of medium. For obvious reasons, we'll start by assuming this propagation occurs at the speed of light c. Next, we'll choose to work with potentials instead of force. This is because the electric and magnetic fields interact in complicated ways according to Maxwell's equations. And working with potentials greatly simplifies the picture. Note
Potentials instead of what?
that there are actually two electromagnetic potentials, a scalar and a vector one. But for now, we'll only worry about the scalar one. Now, from electrostatics, we know that the potential falls off spherically as 1 over r about a point charge.
Yeah, but there's no waves. Those are lines. Those are field lines. Oh, come on. Whatever. So scalar potential, that's just the amount of scalar, okay? Terrain of the potential hill. Good. You're not showing a hill unless these are topological lines. Separation between contour lines. Okay, fine. Represents an elevation change of 1 over 10 kilo Q. I don't know what the Q is. It's a potential of it. That's the charge in potential. Okay, 1 over 10th of 1,000 charges. So 0.1 kilo Q, 0.1 kilo Q. Closer lines represent steeper ascent in the value of the potential, hence greater force. Why is it greater force? What do you mean force? What are you talking about? What force? I don't know what force you're talking about. What force? So if you have a test particle here, okay, there's just more lines, I guess. I don't know. I mean, obviously, if you put a proton or even an electron here, let's say this is an electron, you're going to put another electron. Here it's going to feel much more than here. It should drop off as 1 over r. Okay, that's similar to the gravitational field. Okay. Right, it goes to infinity at the center.
But we want to describe the process of how this information actually travels from the charge to the field point. To do this, let's imagine the potential field as being continuously communicated by the charge via spherical waves, whose amplitude falls off as 1 over r.
But that's not how it's communicated. It's not communicated through waves. It's communicated through field lines. You can't communicate waves. Waves are energy. According to you, it's going to lose energy. Oh my God. Did you get it wrong? 956. Jesus Christ. 956. The point charge particle is communicating its potential field via what? Via waves. But waves or carry energy. E equals h nu, hv, whatever, or hc. Wait, hc? No. hf equals hf. So whatever frequency you have energy in that wave, right? So you're wasting energy. It's going to run out of energy. So the particle is going to run out of energy. Hence, this thought experiment is completely incorrect. Gedanken, thought. Does that spell thought? And is incorrect. This is not how charge. This is not how charge is communicated, but rather via what? Via just field lines. Not waves. Waves are communications of energy, of something else, of motion, of change. The fact that the charge is being manipulated. No. The point charge particle is communicating its potential field via waves. So we should say in the, okay, according to the narrator, the point charge particle is communicating its potential via waves, but waves carry energy, E equals hf, so the particle is going to run out of energy. Hence, this thought experiment is incorrect. This narration is incorrect. This is not how charge is communicated, but rather via field lines, not waves. Waves are communicating the fact that the charge is being manipulated. Oh, ha ha ha, yes. All right, I'm gonna go to sleep. I gotta go to sleep. I'm tired, Trinity. Okay, everyone. Okay, we're good. We're good. Okay, it's 2 hours. It's too much. But I'm really curious about this. I really want to know what's going on. This is quantum mechanics. As you can see, understanding Maxwell with just the most rudimentary particle physics is already quantum physics. You already have to deal with extreme complexity that is beyond your wildest dreams, that I don't know if anyone understands it. I don't know. All right, I'm gonna go. All right, everyone. Did we say what we're gonna do next? Next show. Can we use time dilation alone without length contraction to explain? We gotta finish this. But isn't this? This is it. Aren't we doing what we wanted to do? So we just have to finish. We have to finish watching this video. So let's just make a point though. Finish watching. Oh my God, Jesus help me. Oh Jesus, why are you helping me, Jesus? You're not helping. You told me you would help me. Oh my God. Oh my God. All right. So up next. Finish watching dialects. dialects, this, then do this and do that and do this and do that. All right, I'm really tired. You know, when I'm tired, I am in pain, and you can hear my pain. All right, I'm going. I'm really going this time. All right, see you tomorrow. Bye.